We're going to wrap up our module on Chapter 2, this Introduction to Derivatives chapter. We're going to talk again about the instantaneous rate of change, what the units should be, and then how to read a graph of a velocity function. So let's start with the idea of instantaneous again. So yesterday we talked about how instantaneous relates to the word velocity, but now we want to talk about the instantaneous rate of change. And so we say f prime of x. So this is the instantaneous rate of change of f, so that's how you know the letter on the outside, with respect to x, and that's always the letter on the inside. So instantaneous rate of change implies that there's a prime, and then with respect to, we'll always list the variable that goes inside the parentheses. And when we say rate of change, we mean instantaneous rate of change. Okay, the implication, if you don't actually say instantaneous, but just say rate of change, it's the same thing. Now the units for a rate of change, you always look for the units for f, or the units for that function. And so the units for f will always go on the top. So if that's measuring gallons, or if it's measuring apples, or if it's measuring whatever, meters, then the units would go on the top, over, and then the units for that variable, the with respect to, so respect to x, or whatever, then those units will go on the bottom. So that's how you get meters over seconds. Meters would measure the variable on the outside, and then seconds would measure the variable on the inside. So let's go through an example as it has to do with the area of, it's not of a square, cross that out, it is of a circle. All right, the area of a circle as a function of the radius. So we know the formula for the area of a circle is a equals pi r squared. In part A, we are asked to find the rate of change of the area with respect to the radius r. So in part A, we would write that a prime, that's the rate of change of the area, with respect to r would go on the inside, like this. All right, and now we're going to find what that turns out to be. So we take the power of 2 and we pull it to the front, and then we subtract. Remember, pi is just a constant. And so 2 would come in front of pi, so those are the constants. And then r is now to the first power. So this is called the rate of change of the area with respect to the radius. Okay, part B. Evaluate the rate of change when r is 4. So there's the rate of change, and now we want the radius to be 4. So that would be 2 pi times 4, or 8 pi. And then part C, find the units for the rate of change. All right, well, we need to know the units for the outside letter first. So area. So what units do we do for area? Well, the units for area are always a squared unit. Square feet, square meters, square inches, square something. And we don't know exactly what that unit is. It doesn't say in our problem what kind it is, but it is a square unit. Then we need the units for radius, because that is what this is being done with respect to. Okay, the units for radius. And again, the units for radius are just going to be inches or meters or feet, not squared, just plain. And so that would be a plain unit. And so the answer to this question, what would be the units for this? It would be a square unit over a plane unit. So if we were told that this was in feet, it would be square feet over feet. Okay, those don't reduce each other because they're two different things, but square feet over feet. Or if it was inches, it would be square inches over inches. A big skill, huge skill moving forward, is knowing how to read a velocity graph. So if this is not just the graph of a regular function, but if this is a graph of a velocity function, this is a huge skill for you to be able to do. So we're going to break it up into different intervals. The first interval is the interval from -3 to 2. So I'm just going to color code that interval. That is this section. It's like that column. Within this section, oops. Okay, we're looking at this part of the graph from here to here. The velocity of that graph, this is the velocity graph. This is below the x-axis. And so we would put that this has negative velocity. Acceleration, which is the next question here, is the derivative of velocity. And remember that we can replace the word derivative with its synonym, so we can replace that with the word slope. So the acceleration is the slope of the velocity. Okay, as we look at this graph, we can tell it goes down 1 over 1 in that section. And so we would put that it has negative acceleration. Now you don't have to put what it is, you don't have to put down 1 over 1, just positive or negative is all we need. So then let's interpret the next section of the velocity graph. And so let's say, okay, we're going to go this section of the velocity graph. All right, well, so now we're going from the point -2, -1 to the point -1, 0. The velocity itself is still below the x-axis, and so I put negative. But the slope is now up 1 over 1, and so that would give us a positive slope in that region. And then we're going to move across this graph one section at a time. Okay, so this next region of the graph, it's connecting, whoops, let's keep it the same color, to the next point. Now we've crossed the x-axis, and so the velocity is now positive because I'm above the x-axis. But we've stayed on the same slope of up 1 over 1. So that's the combination where they're both positive. The next section of the graph continues in the same pattern. It continues above the x-axis, so that's positive for velocity, and with a positive slope. Okay, next one, we're going to do 1 to 2. So that'll be this region right here. All right, well, this region goes straight across. It is still above the x-axis, so I put a plus. But its slope is not negative or positive. It's straight, it's 0 because it's completely horizontal. So I'm going to put 0 there. So your only options for this chart as you fill it in are either positive, negative, or 0. Okay, let's keep going. Let's do this section here. So this is from -2 to 3. The graph connects at 2, 2 to 3, 0. It is still above the x-axis, but its slope is now down 2 over 1, so its slope becomes negative. You'll get faster at these as you do more of them. Okay, we'll color code that one from 3 to 4. It now crosses the x-axis, so it is negative velocity, but it continues to have a slope that goes down 2 over 1, so it still has negative slope. From 4 to 5, this region in here, the graph itself goes directly horizontal. It is still below the x-axis, but its slope is 0 again because it's completely flat. And then from 5 to 6, this region here where the graph itself starts to go up, it is still below the x-axis, so that's the velocity, but it has a positive slope. And the last region next to that has a similar behavior. It is also still below the x-axis, but it has a positive slope. Once you have your chart filled out, then you can answer all the questions that you'll need to know about that particular chart. So I've transferred this chart onto the next page. The most important things about this chart are going to be where the velocity row changed from one sign to another, and then another change here. And so that's where I've added red lines to my chart to help me see that it is definitely changing direction. Okay, the direction is always connected to the velocity. Okay, so you could cross out the word direction here, and you could do change velocity. That is the same question. And so I'm changing velocity at time equals -1 because the values of v changed from minus to plus, from negative to positive. And then again at time equals 3 for a similar reason, not exactly the same, but because the values of v this time changed from positive to negative. And then when is the particle going to the right? So the particle is going to the right every time the velocity has positive values. So all of these values right here represent the entire time interval where the particle is going to the right. Positive velocity means going to the right. And so it's going to the right it starts going to the right at -1, and then through 0, and then through 1, and then through 2, and all the way to 3. It goes right from -1 to 3 because the values of v are positive. So then when is it going to the left? Well, it's going to go to the left anytime the velocity values are negative. And so we've got two sections of intervals where the particle is going to the left. And so we'll say it's going to the left from -3 until -1, and again from 3 through 4, through 5, through 6, and then all the way to 7. And then the reason is because the values of v are negative. Maybe it's better if we write the word negative. And then what about stopped? So we answered right in the red, we answered left in the green. Okay, what about when the value is stopped? Okay, well, it's only going to be stopped when it's changing from going to the right to the left. It doesn't happen for very long. It only happens just for a moment. And so it's stopped momentarily or instantly. Instantaneously, maybe we'll say. And it's only stopped instantaneously at -1 and at 3. Okay, it's the same places, basically it's the same answer as it was to the first question. Okay, those are, when is it change velocity is the same time as when it stopped, because it's having to pause a moment, but it happens so fast you can't see it with the naked eye, but that's when it's changing its velocity. All right, this is the same graph, the same chart again. Now we are asking the questions about speeding up. Remember from yesterday, speeding up is when the velocity and the acceleration have the same sign. And so we look through and we see that the velocity and the acceleration have the same sign, where they're all pluses right here. And then again, the velocity and the acceleration have the same sign, where they're both minuses. And so it's speeding up from -1 and through 0 up to 1, and again from 3 to 4. When is it slowing down? Well, it's slowing down. Oh, I see another one. You guys probably already saw it. I missed it. That one. So it's speeding up there again, and from -3 to 2. Okay, slowing down. Slowing down is when the velocity and the acceleration have opposite signs. So the velocity and acceleration, opposite sign. Okay, so that would happen this time interval, opposite, and this whole time interval again. So that'll be from -2 to the time interval of -1, and from 2 to 3, and from 5 through 6 up till 7. The last question, when does the particle coast? Coasting is the same as 0 acceleration. And that happened twice. It happened here and here, where we had 0 acceleration. Doesn't matter what the velocity is doing. It just matters what the acceleration is doing. And so that would be from time 1 to 2, and again from 4 to 5. So once you have a table set up or a chart set up of the velocity and the acceleration values, it's really, you just got to read the graph and look for the right combinations to answer your questions. So let's try reading another velocity graph. All right, so let's look at from 0 to 1. So that's time 0 to 1, which is the section of the graph which goes from here to here. Now that's above the x-axis, so I put a plus. It also is curving up with a positive slope, so I'll put another plus. Then we go from 1 to 2. That's the next interval up to this point. It is still above the x-axis, and it still has positive slope. Then we'll go from 2 to 3. It is still above the x-axis, but it has negative slope, so something changed. And then from 3 to 4, it is still above the x-axis, and it still has negative slope. From 4 to 5, still above the x-axis, 0 slope. 5 to 6, above the x-axis, 0 slope. 6 to 7, above the x-axis, negative curve of a slope. From 7 to 8, I have now crossed below the x-axis. So I am going to put a red line right there because that is the most important point of this graph, where it crossed from above the x-axis to below. It continues to have negative slope. From 8 to 9, it is below the x-axis, but changed to positive slope. And then from 9 to 10, it switched again to being above the x-axis. So I'm going to add another red line here because again, that is an important place, and it has positive slope. So just break it up into intervals. Then use that to answer the next set of questions. Okay, once again, I'm going to add these red lines here because that represents a place where it changed from plus to minus and again back from minus to plus. So that answers the questions for me. When does the particle change direction? And it's happening at time equals 7. The velocity changed from plus to minus, from positive to negative. So that means that the direction is changing from right to left. Actually, up to down. Okay, changed direction. But it changed again, right? It changes again at time 9. I'm going to have to squeeze this in here. At time 9, the velocity changed from negative to positive. So the direction changes. From down to up. All right, that's directly really connected to the next question. Well, when is the particle going up? All right, going up is the entire time that the particle had positive velocity. And then again, this little one at the end. So it's going up from 0 through 1, 2, 3, 4, 5, 6, and all the way up to times 7. And then it's going again up just in the little interval from 9 to 10. So this is going up for a while, and then it goes down for a little bit, and then it goes back up again. So when is it going down? I'll do that in blue. Down is the negative velocity. So down is from 7 up till 9. And then stopped Stopped is correlated directly to these same two positions again. So stopped would be at time equals 7 and time equals 9. So notice that stopped is the only one that's answered with equal signs, but up and down are answered as intervals, okay, with inequalities. Here's the same graph again. Okay, we're asking the questions about speeding up and slowing down. So speeding up is looking for places where the velocity and the acceleration match each other. So speeding up is going to be that interval. And then again one more time here. So speeding up is going to be from 0 through 1 up till 2, and again from 7 to 8. And if you had to answer why, it's because it's the same sign of the velocity and the acceleration. Slowing down will be the intervals where we have opposite velocity and acceleration values. Oh, did I forget another one? I did. Plus to plus and 9 to 10. All right, now we've got our minuses. So slowing down. See how easy it is to miss them? So just double check. From 2 through 3 up till 4, and again from 6 to 7, and again from 8 to 9. Okay, and then coasting will be places where the acceleration was 0. Doesn't matter what the velocity is doing for coasting, just the acceleration.